Hi everyone, I am Tarun Khandagare working as a senior software engineer in Visa. Today we are going to solve very famous problem which asked by multiple product based companies in the interview rounds. The problem is flatten the binary tree to linked list. So let me explain what problem actually saying and what to do in our problem. Okay. So in the question, binary tree coming as input. Okay, this is our binary tree which came as input. Okay, and we have to convert this binary tree to linked list. Okay, and our output looks like this. Now question here is how we are going to manipulate this binary tree to linked list. Okay, the constraint here is we don't want to change our binary tree structure. Means what binary tree structure follows? Binary tree contains left and right node. Okay, and value of it. This is our tree node structure. Okay, this binary tree follows. And what is linked list structure here? If you see linked list structure contain value of it and the next pointer. Okay, so what question is saying, we don't want to change this structure, but we need to convert this binary tree, so when we are going to traverse it, the output looks like a linked list. Okay, now question is how we are going to do that. Okay, now question here is how we are going to convert this binary tree into a flattened linked list. So let's consider I want to traverse in the binary tree and I want to traverse using pre-order traversal. Okay, so how pre-order traversal works? Pre-order traversal print the root node, then the left child, then the right child. Okay, so it will print 0, then came down, it will print 2, it will print 3, it will print 4, it will print 5, and at the end it will print 6. So this sequence is followed here also. This linked list is follow this sequence. Okay, that we are clear on that. We saw the pattern. Using pre-order traversal we can able to derive this sequence. Okay, now what we have to do actually, one node contain null, 2 dot contain null, 3 also contain null, 4 also contain null, 5th also contain null, 6 also contain null at the left node, at the left side of it. So this is the node. If I consider this node, this contain the right value, this contain the left value, and left value is null. That's why this tree looks like a flattened linked list. Okay, this is also a tree. Okay, this is the root node of tree, but here as you see the left subtree and the right subtree. With the help of pre-order traversal we take these nodes and try to manipulate this node and print in the form of this sequence. What is here? Now the question arises how we are going to convert this binary tree into a flattened linked list. What is the logic behind it? Every student I guess got to know that this is the left child of it and all the left child of it is null. That's why the structure of it looks like this. Okay, so that is the demand of question. We need to take every left child of binary tree and add it at the right side of it. Okay, so the binary tree looks like this, and this is the perfect flattened linked list converted by binary tree. Okay, converted with the help of binary tree. Okay, now come here how we are going to develop this logic. So how we are going to develop this logic? For developing this logic actually we want a binary tree, and we start from the root. Okay, we are trying to do a pre-order traversal. Okay, using pre-order traversal, first root is came. Okay, so what we do, when root came, we directly add root to the output. Okay, when 2 came, we add this 2 at the output. Okay, but how we are going to do that, how we are going to do that, that is the main concern here. Okay, so how we are going to do that, what we do is we take one stack. Okay, stack, you can use separate stack also, or we can use the recursion stack also, that created by recursion. Okay, so what we are doing, using pre-order traversal, we have to traverse on the binary tree and store these values like 1 2, then 3, then 4, okay, then 5 and 6. Okay, we store all the values in the stack. Now let's consider, okay, take this top value, okay, and add it in your output. So I add it. Okay, now maintain previous. Okay, previous equal to null and current value. Okay, current equal to stack ka top. Okay, stack st top. Okay, I maintain these two values and stack current value is here, and we will pop these values from the stack. Okay, this getting popped. Okay, when the new values came, okay, when the new value came, this all, this is running till when stack is not empty. Okay, this I got that, and preview equal to current. Okay, now let's consider the new value came, stack top is 5. Okay, now 5 came. So what we have to do here, the sequence of output looks like 1 2 3 4 5 and 6. So by seeing this, 6 is here. Okay, 5 is on the stack dot top. Now we have to connect this 5 to this 6. So how we are going to connect this? Okay, so when 5 arises, this is our current node. Okay, got that, and this is our previous node. When current dot write connected to previous, when current dot write equal to prev. Okay, and we have to always say current dot left equal to null, because current dot left doesn't contain any values. That's why we are saying it is a flattened linked list. Okay, that thing also I got it. Now the next turn arises. Okay, when the next turn arises, this prev is here, and we will pop the next stack element. What we will pop? We will pop this 4 on the top. So we will make as current node. Okay, we make as current node, and this is our prev. So prev equal to current. Okay, we forget to pop the element here, so st dot pop. Okay, now previous here current element is 4. By seeing this, okay, current dot write equal to prev, by using this we are connecting 4 to 5. Okay, we are connecting 4 to 5. Okay, and by doing that we are saying ignore or put null as at the left child of 4. Okay, so we put that also clear. So like that every node, okay, by using these conditions as I mentioned here, by using that conditions every node is filled, and at the end our root node looks like this. Root node is 1, root left is null, and root right contain 2, then 3, then 4, then 5, then 6, using pre-order traversal. Okay, using pre-order traversal, we are maintaining the sequence in the stack. We are popping one element from the stack and make that element as last, and when the new element came, we will connect that last element to the new element, okay, at the right side of it, and then the new element become the last element, and then again we are popping from stack and make the new element as I mentioned here. Okay, by doing this, how we are going to do this? Till that time when the stack is empty. If the stack is empty, that makes sure that our possibilities are done, we are got our answer. Okay, so this thing we are going to see in the code on the website lead code. So let's go on the lead code and try to run this code at the lead code and try to compile it and submit it. Okay, so let's discuss about the time complexity of it. So time complexity is big O of n, and the space complexity is also big O of n, because we are maintaining the stack, we are maintaining the recursion stack. Due to this the space complexity is O n, and the time complexity is also O n, because we are running the loop on it. Okay, so hopefully you got that. Let's try to run it and submit it on lead code. So as you can see here, this is our code. Okay, we are maintaining one stack to store the pre-order traversal of it. We are calling the pre-order traversal and try to store all the element in the stack. So at the end, this 6 will be our top element. Okay, the same thing we are doing. We are popping one element from the stack. We are doing pop. We are considering top dot write as last. Okay, so at the first time when the 6 came, the top dot write means we are setting to last, and last is null. So at the last element, left and right both become null. So we are setting that things, and at the last we are saying this 6 become our last element, okay, or previous element. When the new value came, this 5, so 6 is last element, okay, and 5 is topmost element. So we are connecting this 5 to this 6 by using this statement, and we are making the 5 left child as null. Okay, so this will go again and again till that time the stack is empty, and when it is empty we are make sure that our flattened linked list design is ready, code is ready. The time complexity of the code is big O of n, space complexity of the code is also big O of n. So let's try to run this and check whether our output coming correctly or not. So as I see here, it is accepted, means everything going correct, case 1, case 2 and case 3. Let's try to submit it and check whether all the test cases are passing or not. So as I see here, all the test cases are getting passed. So hopefully we got our answer. Here. Let me explain one more time what we are doing here. We are doing the pre-order traversal on a binary tree. Then using that traverser, we are storing that values into our stack. So the last value will be our top, and using that last value we are connecting this 5 to 6, then 4 to 5, then 3 to 4, then 2 to 3, and 1 to 2 using a stack, as you can see here. So hopefully you understand the solution. I think that you got the solution. The time complexity of it is big O of n, and the space complexity of it big O of n. So hopefully you got it correctly, you understand thoroughly. Let's try to jump on another problem in the next video. Take care, bye bye, see ya, have a good day.